I'm very happy to introduce Valentin Bonzom from the Laboratoire d'Informatique de Paris Nord. He's been working on plenty of things from loop quantum gravity, spin foam, tensor models, combinatorics, topological recursion, plenty of interesting stuff. And he will tell us today about combinatorics of triangulations for quantum gravity.
Thank you, Eta, for the introduction. It's very nice to be here. So I'll be talking about combinatorics of triangulations in the context of quantum gravity. And I have first a quick disclaimer about what this lecture is and is not. And it's probably a good time to thank the organizers and all the lecturers that came before me, because now I guess that you all have a good picture of both the main ideas of loop quantum gravity and also technical aspects. In particular, you will find useful for this lecture to remember what Maite Dupuy talked about and Edward Wilson-Ewing, obviously. However, I imagine that some points might have remained unclear, both conceptually and technically. In particular, when you heard about spin foams, whether you have to sum over spin foams, or how do you do that? Do you have to consider some... Yes?
Valentin, sorry, somebody's asking if you could make the slides full screen.
Unfortunately, I cannot make it larger. We tried with Pietro this morning, but this is full screen for me.
Okay.
Sorry. So if anyone knows about how I can make it bigger with this software, you can let us know. But here, this is the full screen button, as you can see. Toggle full screen, and it's on. So yeah, do we have to renormalize when we sum over spin foams? And if you think about renormalization, it means there are probably some kind of continuum limit. So I will try to discuss those questions using the examples of two-dimensional quantum gravity and three-dimensional quantum gravity. And I will focus on triangulations rather than spin foam amplitudes. So it's going to be a little bit different from probably, I guess, what you've heard before when there are a lot of talks about how do you define the spin foam amplitudes. But here, focus will be on the more combinatorial objects. Also, my conclusions might not be super conclusive because I will consider different examples, which are quite different indeed, and different methods that I use to treat them. And the contact between those methods is still an active topic. At least I will have some mathematical answers in the form of theorems. However, no definite answers to conceptual issues, as I say. So hopefully this will be a mix of technical and conceptual issues and questions that will keep the lecture interesting for both young and more experienced folks. And I also have to address the issue of false advertising, because you saw my title is not the title that you were promised, because you were promised group field theory and renormalization. So GFT is group field theory, and apparently you've been lied to. In fact, not so much, but I will postpone renormalization of GFT to the very end for mainly three reasons. One is a weak reason, which is not that it's not exactly my expertise. So obviously I'd rather talk about something I'm super familiar with. And although, yeah, I can probably understand most of what people do in GFT renormalization, haven't contributed too much. The second reason is more practical, is that it's a field that's very heavy on field theory calculations and methods. So, I think that could really quickly become very heavy. And the final reason is more conceptual, because I think there are important things to understand first in order to get a clear picture of the big picture, if you want, before really going into something as complicated as renormalization, whether it's in group field theory or more generally in loop quantum gravity. So let me first start with transition amplitudes in loop quantum gravity. And you know, thanks to Maite Dupuy, I guess, that the Hilbert space is spanned by spin network states, which are decorated graphs. So in principle, I can annotate. So spin network states are decorated graphs, which means graphs with spins on their edges. And obviously you want to calculate transition amplitudes. Let's say between a spin network gamma 1 to gamma 2. So gamma here means a graph with spins. So that's also called the physical scalar product. And the reason is that you take those two states, gamma 1 and gamma 2, and then you know that the Hamiltonian constraint, that the Hamiltonian is in fact a constraint. So basically what you want to do is take a state, let's say gamma 2, and project it onto a subspace where the Hamiltonian vanishes. So here it's formal, obviously, because delta of h equals 0 is not super well defined, let's just say. But at least formally, I can expand this delta function using fictitious variable t, which actually should be the shift n from the point of view of general relativity. So here it's integral dt, and I have exponential ith as an operator. So when you want to go to spin forms, what you do is basically use a path integral representation. So you slice t into intervals of a small size delta t. And at each step, you insert a resolution of the identity as the sum of her spin network states. So basically on the picture in the right here, you can follow t goes upwards, and you start with the graph gamma 1. And then you let it evolve under this evolution operator, exponential ith. So here, let's just say that until this vertex v in the middle, the evolution is kind of trivial because you still have always the same graph, and we can assume that the spins don't change. So basically, we have, when we consider this exponential I delta th, for part of the evolution, this will be trivial. And so gamma 1 and gamma 1 prime will be the same, and so on. And the same happens close to gamma 2 here. There's no changing of the graph gamma 2 between this vertex v and the top of the picture. However, there is a vertex v here where the graph changes, and this is where you have a non-trivial action of the Hamiltonian operator, presumably. Okay. So basically, this picture is supposed to give you a visual representation of how the path integral representation works for spin network states. What happens is that you build out, so you have two graphs on the boundaries and a two-dimension complex between them. Okay. So when you do this evolution, you start with a network, and it has vertices and edges. When they evolve, you get something that's called a spin foam, and a vertex becomes an edge when it evolves. Sorry. And an edge becomes a face. So that was represented here by this pink area here, which is a face of the foam. And then when you want to change the spin network, you need a vertex in the spin foam. So eventually, because it's like a path integral representation, you want a sum over spin foams, which means summing over decorated two complexes, gamma, capital gamma this time. And so you do this sum with an amplitude A of gamma, which interpolates between gamma 1 and gamma 2. Questions? What is the set of spin foams that you have to sum over? Now, this is quite a big question because, in fact, if you look at what I did in the previous slide, it was completely formal. So there's basically no first principle derivation of the set of spin foams because here, this object, we don't really know how it acts. There's no satisfactory quantization of the Hamiltonian constraint. So eventually, we don't know what the class of two complexes is. So then you might ask, well, okay, maybe there's some principle that can guide us. And one of them could be having a field theory, which is the case for group field theory. Now, I will give you another argument, and I will try to make the case for triangulations. And for me, an important aspect, I think, is to recover the metric picture in some limit. So if you start to think about how loop quantum gravity is supposed to give you quantization of general relativity, you realize that you have two degrees of freedoms in loop quantum gravity, the spins and the graphs. And obviously the spins live on the graphs. But it's more actually three types. So here, DOF means degrees of freedom, okay? Degrees of freedom. It's more actually three types of degrees of freedom because you have boundary graphs, which are spin networks, and bulk graphs, which are spin foams. And so the way geometry is encoded is through the spins. So when you have a graph, let's say like here, some kind of tetrahedron, for instance, is decorated with spins. The spins and the intertwiners encode the geometry, but it's not degenerate only on the graph, meaning that, so if this is my manifold somewhere like this, and I consider a region here, which is far away from the graph, then basically the metric is zero. So basically not a metric. So it's completely degenerate elsewhere. Now, if you want to recover some metric picture, it means you want states to basically cover the whole Cauchy surface that's used for the Hamiltonian quantization. So only then you can recover a metric picture in some sense. And you also want the spin foams to capture the topology and the geometry of space-time itself, okay? So basically, this means it's a good idea to consider triangulations because they are both graphs, so we can use them in the context of quantum gravity, and they're also manifolds, piecewise linear manifolds. So it means we encode all the topology through them, and if we consider triangulations, we have maybe some chance to recover metric picture at some point. Obviously, that would involve some kind of continuum limit with these two types of degrees of freedom that I talked about, spins and graphs, which is complicated, obviously. Now, let me give you a tour of triangulations in the context of quantum gravity. So first, it was quite a successful story in 2 dimensions. And the model I will talk about in this lecture is the model of combinatorial maps, where you build the space-time geometry by gluing triangles, squares, and so on, or polygons in general. So here on the right-hand side, I tell you for each model what kind of degrees of freedom you have. And for combinatorial maps, you have no spins. You have only graph degrees of freedom. Now, there are other models of random geometry in 2 dimensions, and I just want to cite one, which is based on Delaunay triangulations. It's a model from David and Enar, and it's very interesting because it uses length and triangulation degrees of freedom. So you have triangulation and length decorating the triangulations, but you also have changes of triangulations in this model. And I think that's a very interesting model that's been a little underappreciated or overlooked in many communities. including by me. I just think it's interesting. I haven't done anything on it. Now, in high dimensions, let's say in 3D, what is a triangulation? It's basically a gluing of tetrahedra. So you take tetrahedra and you glue them. I will have many pictures later. However, it's very hard to define models of random geometries in 3D, which are both solvable and non-trivial. Like I will give you some models of rings of tetrahedra, which are non-trivial to solve, but still is possible. But if you think about it, there is some kind of triviality in them eventually. So yeah, it's difficult to have something that's both solvable and non-trivial. We have a couple of interesting models and probably more. I just want to cite here dynamical triangulations where you have no spins and only graph degrees of freedoms. So this is like the counterpart of combinatorial maps in 3D, the extension to 3D extension. And also we have three-dimensional quantum gravity, where it's a bit of the opposite situation, where basically the graph is fixed, the triangulation can be fixed, and you only have spin degrees of freedom. However, so there's a little footnote here, which I think is pretty important, is it works as long as the graph is a triangulation, otherwise you do not capture the topological degrees of freedom. So this is part of my case for triangulations. Okay, so we have models which capture different types of degrees of freedom in 2D and in 3D. And now what about full quantum gravity, let's say? So there is some tricky interplay between spins and graphs, DOFs. So the way loop quantum gravity works, I think if you look at a textbook, you will find that it starts with generalized holonomies, which are ways to assign group elements to path and edges. Okay, so when you have an edge like this, and you get a group element G for the path gamma, which is a holonomy. So it might look like a discrete theory because we have graphs, but in fact, there's been quite a lot of work to emphasize the fact that it's a continuous theory because all graphs are considered, not just one triangulations, but just all possible graphs. On the other hand, we have something that you were probably presented, I think, by Edward Wilson Ewing, which is a Regge calculus, where it works on a fixed triangulations. Okay, so it's an approximation of general relativity, where you use its length. So basically the partition function Z depends on the triangulation delta. So that's the triangulation delta. You integrate over the length of the edges. And the Regge action, here it's the Regge action. It discretizes the two types of terms from the Einstein-Hilbert action. So you have one term where you sum over the so-called hinges or simplices of dimension d-2, the volume times the deficit angle around them, plus the volume term, which is here the volume of the full space-time manifold, and lambda is basically the cosmological constant. So this is a model for discretized general relativity, and it was realized that loop quantum gravity on a fixed delta is basically like a quantization of GR on that triangulation. So basically, if you look at loop quantum gravity on a fixed triangulation, it's not really an approximation, because from the point of view of loop quantum gravity, you should consider all graphs. And if you look at just one graph, it's difficult to see what kind of approximation you do. So it's more often called a truncation, because you restrict to a single graph. And when you do that, it means you work with the Harmony flux algebra on that triangulation, and you can interpret it as a discretization of Palatini or Plebanski action. Okay, so so the plan is to study triangulations first in 2D quantum gravity models using combinatorial maps, then in higher dimensions, and eventually, if I have time, we'll look at group field theory and its renormalization. A reminder, because we need quite a lot of mathematics here to discuss triangulations. So I want to remind everyone of the classification of compact oriented surfaces. So it's textbook material that every surface is homeomorphic to either the sphere, which is said to have genus 0, or the torus, which is said to have genus 1, or a more general surface with a certain number of holes, which is an integer h, and it's called the genus. Okay, so h here, in my notation, will be the genus. And here, this is like from Wikipedia. If you look at the genus of a surface, you will find this picture of a surface of genus 2, which has 2 holes. Okay, so that classifies it. Now, I want to emphasize the effect on dimension, because I told you that we have different models in 2D and 3D with different types of degrees of freedom. And the dimension is crucial. So first, let's have a look at two-dimensional gravity on a Riemannian surface. So this is a Riemannian here, not Lorentzian, of genus H. And here I've given you Einstein-Hilbert action in 2D. So you've got the two usual terms, curvature term and area term, or volume. And something happens in 2D, which is very crucial, and that's the Gauss-Bonnet theorem. It tells you that the curvature term here is actually a topological quantity. It's just basically the genus. It's 1 minus the genus divided by 2g. So it's constant. It does not depend on the metric. So basically, you are left with the area term if you work at fixed genus. So the classical theory is trivial. Basically, all metrics are equivalent. There's no classical theory. However, the quantum theory is non-trivial for several reasons, and I will probably just tell you one of them. And it's the fact that you have a measure on the space of metrics up to diffeomorphisms. And that will give you an interesting theory to look at. So here it's an integral over metrics, exponential minus some constant beta times the area. So beta is this, lambda over 8 pi g. And so you can perform this integral in 2 steps. Let's say you take a value that you call capital A here, and you say, I want to integrate over all metrics at fixed area. So here it's an integral at fixed area equal to this value capital A. And then you integrate over all values, all possible values of the area. So basically what this decomposition shows you is that you work indeed with the uniform distribution of a matrix of fixed area, okay? Because here this is delta. So uniform distribution of a matrix of fixed area. And then you take the Laplace transform. So here, this is Laplace transform. Okay, so that.
Valentin, that's a question. What is the metric that you are using here? Is it plus plus?
Yes.
Thank you.
Riemannian. Yeah, more questions? Okay, thanks.
No, you can go ahead.
So plus plus because basically in that case we know a lot of things, and we know how to write the integral of a two-dimensional matrix on the surface of genus H. It's well known after a lot of efforts from the mathematical community. You know that in fact you can decompose the space of matrix into first the set of conformal classes and the conformal factors. So basically you say that G is a conformal factor times G0, which represents some conformal class of matrix in 2D. So this space of conformal classes here, it's known to have dimension 6h minus 6, and then the conformal factor is just a real function. Okay. Now in higher dimension, things can be quite different. So let's look at Einstein equations. Here, when you take the trace, you get the curvature R, which is found to be constant, linear in lambda. And if you add the fact that you're in 3D, let's say, you have a new relation which expresses the Riemann tensor as a function of the Ricci tensor. So this is a relation that I wrote here. I left some parts unwritten because it's a long expression, but nothing too scary, only 4 indices. Now, if you mix those 3 equations together, meaning that you indeed restrict to 3 dimensions, you find that Einstein equations only have de Sitter or anti-de Sitter solutions, depending on the sign of lambda, or flat if lambda equals 0. So these are de Sitter or ADS solutions. Okay, so that's these are solutions to Einstein's equations. What about the space of metrics? Well, in dimensions higher than 2, it is quite complicated. Let's say you're in 3D, the space of 3-dimensional metrics, it's been studied quite a bit by mathematicians. It's called something called Thurston geometrization, and it started with the Poincaré conjecture a long time ago, evolved into a geometrization conjecture by Thurston that was proved eventually by Perelman. So yeah, basically, space of 3D metrics is complicated. Also very different from 2 dimensions, and depending on boundary conditions, I will explain. So let's imagine first that you look at a closed hyperbolic manifold of dimension d greater than 2 and a finite volume. Then there is a quite famous theorem that's called Mostov rigidity. And it tells you that basically the space of metric of constant curvature -1, because it's a hyperbolic manifold, it's a space with a single point. There is a single metric of constant curvature -1. No possible deformation. So this is very unlike the 2D case that I just showed you before, where you have a moduli space of conformal classes of dimension 6h minus 6. So here it's a point. There is a single metric. Obviously, it depends on the assumptions that I started with. So if the volume is infinite or if it's not a closed manifold, it can be very different. So just something to keep in mind, that the dimension is important in quantum gravity. In 2D, we have this modular space of conformal classes and conformal factors. But in 3D, it's more complicated. You have 8 model geometries that I will not talk about. It's everything proved by Perelman eventually. And classically, you have Einstein equations. In 2D, all metrics are equivalent. And in 3D, you only have constant curvature metrics. So very, very different set of classical solutions. In the quantum theory, it means that in 2D, you have a uniform distribution over metrics of fixed area. But in high dimensions, it depends on boundary conditions. And I guess that's something that's been discussed by Mark Zeller in his lectures. So widely different theories in 2D, 3D, and 4 dimensions. Can we expect similar quantization methods to work? I do not know. How important are the boundary conditions? Probably very hard to say more for me at the moment. So let's start to look at different models in details and prove theorems. So here's the model of combinatorial maps. It's completely combinatorial. You take polygons, like here, hexagon in teal, pink triangle, and orange square. And the errors here means that you identify the edges on the boundary of these polygons. So when you identify, it's like saying you glue them and you get something like this. So here, this vertex here is pinched because you glue the two edges incident on it. So it gives rise to this vertex here. And when you follow the inside of the polygon, you have to go around like this. Okay. You can check that here the orange part has 4 boundary edges, so it's indeed a square. And so, as I tell you, if you follow the inside of the teal polygon here, you find that it's a hexagon. So there's a partition function for combinatorial maps, which are here called Boltzmann maps because they have arbitrary weights. So it's a function that depends on an infinite number of parameters. How do you build it? It's a sum of maps, which are these objects. You can ignore the automorphism group for now. Then you have m to 2 minus 2 times the genus. So it's something that would be n squared for sphere, n to the 0 for torus, and so on. Okay, so it's a 1 over n expansion with respect to the topology. And then for every polygon of size k, you put a weight tk. Okay, so eventually you have tk to the nk, where nk is the number of k-gons. Okay, so here in this example you would have t6, t3, and that's t6, and here it should be t4. Sorry. Okay. And there's a final t that I just forgot, which is t3 on the boundary, because on the exterior here, you also consider that it's a face, it's part of the surface. So, and the boundary has length 3, so it's a t3 on the boundary. Now, how do you get a quantum gravity interpretation out of that? Well, from the Gauss-Bonnet theorem, you know that if you have something to the power 2 minus 2h, it's basically the integral of the curvature. Okay, exponential of the integral of the curvature is n to the 2 minus 2h. And if you say that this coupling tk, this weight on k-gons, is proportional to exponential of the area of the k-gon, then the product is the whole area. Okay, so basically the tk are exponential of the area of the k-gon. So this gives you quantum gravity interpretation, and it means also that because it's a discrete model, you need some kind of continuum limit. And to discuss this in further detail, I will even simplify the model further and tell you about binary trees. So this is my training exercise, if you want. So what's a binary tree? It's a graph where you start at a root here. And a node can have either 0 children, like this one, 0, 0 child, or 2. So it can have either 0 or 2 children. No cycle, that's why it's a tree. There's a notion of size, which is the number of internal nodes. So internal means those who have children. And I would denote Tn, number of rooted binary trees of size n. and then form the generating series T of Z, sum over n Tn Z to the n. And it's the same as saying that you sum over all binary trees, rooted binary trees, with Z to the size of the tree. Okay, so here it's size of T. Okay, so in more physical terms, you may say that Tn is the canonical ensemble because you have a fixed number of nodes. You know, you have many trees with a fixed number of nodes. And Tz is grand canonical in the sense that you do not fix the number of nodes anymore, but you have a chemical potential instead, which is Z. Okay, Z is a chemical potential. So now to get the continuum limit, you need to do two things. Two ingredients. You need to let the size of the trees goes to infinity, which means n number of internal nodes goes to infinity, meaning that you look at the asymptotic regime. Okay. You need the asymptotics of Tn. Okay, but that's not enough. If you do that, you're just going to have an infinite tree, okay? And that's called the local limit. So this would be the local limit, where you have an infinite tree. So what you want is to have finite distances on your tree. So you introduce some edge length, small a, and it has to go to 0 so that distances remain finite when n goes to infinity. So it requires some special scaling behavior, which is known to be a going like 1 over square root of n. Okay, that's a known fact that I will not prove. Okay, so how do you? So I will need basically from the mathematical side, I will need the asymptotics of Tn. And for this, it's useful to know some transfer theorems, which relates the asymptotics of Tn, of the number of objects, to the critical behavior of T of Z, generating series. So let's skip through Pringsheim's theorem. Maybe I shouldn't go too technical, and just give you the transfer theorem. It tells you that it's equivalent for the generating series to have this kind of singularity, rho minus z to the alpha, where rho is the radius of convergence of the series. And having a singularity with exponent alpha is the same as having this asymptotic behavior. So here, I can tell you that's a constant, so you couldn't care less. Here, it's some exponential growth. And this is a power law that depends on alpha. Depends on alpha. Okay, so basically the exponent in the singularity, you recover it in this power law decay here, n to the minus alpha minus 1. And the proof is not too complicated. I'm giving here the reference because it's a very classical book, Analytic Combinatorics by Flageolet and Sedgwick. So the basic idea of the proof is Cauchy formula that Tn is a contour integral over 0 or around 0 of T of Z dz over Zn plus 1. Okay, so you have a contour around 0 like this. And what you will do is that because T of Z is analytic until everywhere except rho, in fact, you can deform the contour. Okay, so deform the contour to something like this. So here is rho, and so the contour, you will get it bigger and bigger like this, but you cannot go, you cannot pass through rho. Okay, so when you deform, you still have to go around rho. So basically, eventually, you will see that you can have a contour that goes like this. Okay? And if you want the rest of the calculation, you have to look at the books because it's a bit tricky eventually. So you deform the contour, but you have to do it in a smart way. Okay, now we have tools to calculate things. And in fact, it will not be very difficult, I expect. Binary trees satisfy a recursion. So if you have a tree of size n, can be either, so remember every node can have 0 or 2 children. So if the root has no children, you get this, okay? Obviously, n has to be 0 because this is just the root with no children. But if the root has 2 children, one of the children here on the left can have a smaller tree attached of size k, and the right child can have a smaller tree attached of size n minus k minus 1. So this gives you the recursion that's written here on the right. Okay, when you go to generating series, so basically you you multiply by z to the n and sum over n, you get a quadratic equation on T. It's quadratic because there are 2 subtrees in the picture. So you get a quadratic equation on T of z, which you can solve without difficulties, and you get the square root singularity here, square root of 1 minus 4z. So it means that we can apply the transfer theorem with alpha equals 1/2, but you can also, just apply, just do a Taylor series of this square root and find that the Tn are Catalan numbers. So here it's 1 over n plus 1 times binomial coefficient. So whatever you do, you finally arrive at the asymptotic behavior of Tn, which has indeed an exponential growth 4 to the n and some power law decay n to the minus 3/2. Okay, so like I said, asymptotics is key ingredient for the continuum limit. But when you look at this calculation, it seems like it really depends on the model. So what if I change the model? So say instead of binary trees, I look at ternary trees which can have 0 or 3 children. Well, obviously the calculations are going to be different, but at large scale, what do you expect? So in fact, it's reasonable to expect universality. And here, universality means exactly the same thing as in statistical mechanics. It means that quantities that you evaluate at the macroscopic level are independent of the microscopic details. So in our situation with binary trees, it means that if you change binary trees to any reasonable family of trees, you will still get the same asymptotic behavior. And it means in this form. So T of n will be some constant here, which depends on the family of tree, some exponential growth also depending on the family of tree, but this is universal. Okay, this is an exponent minus 3/2, which is characteristic of trees. And many other family of trees will have this exponent. So now that you understand the asymptotics and the fact that the asymptotic has some universality properties, you expect those universality properties to pop up in the continuum, okay? And in fact, they will give you a universality of the scaling limit, of the continuum limit. So usually universality comes with scaling invariance in the continuum, which means that basically when you go to larger and larger scale, you have a renormalization group flow where you go to the infrared. And obviously it makes sense that when you can't go any further because you are at completely large scale, well, you have a fixed point, meaning that you have scaling variance, okay? So as an example, in any reasonable model for ferromagnetism, if you start at low enough temperature, well, you're going to have some tiny fluctuations of the microscopic degrees of freedoms. Like in the Ising model, you're going to have spins which move a little bit, but not too much because it's low temperature. And then when you go to large scale, what you see is mostly frozen regions. So all those fluctuations, tiny fluctuations, they are washed away by the renormalization group flow in the continuum. And so what you end up is with a frozen phase at just like T0 temperature, okay? So this is the effect of the renormalization group flow. And we'll see, so it sort of explains the universality of the scaling limit. Okay, what's the scaling limit for binary trees, or more generally random trees? It's given by Aldous' theorem, which is the convergence of sequences of random trees to something called the continuous random tree, so CRT. So here's a simulation. So there are lots of nodes. I can't remember how much, but it's like several thousands nodes.
There is a question, Valentin.
Yes.
If you can say a word about UV renormalization.
No. Only the renormalization group flow only goes to the IR. So UV is basically just a discrete model that you start with. And the renormalization group flow only goes to in the direction. It's not a group, it's a semi-group. You cannot go backwards. So you only go to the IR.
Thank you.
So this is a simulation of the continuous random tree. Distances scale like square root of n, where n is the number of nodes, and it has Hausdorff dimension 2, meaning it's a fractal object. Like you would think a tree has dimension 1, but the continuous random tree does not have dimension 1, it's dimension 2. It's Hausdorff dimension. Okay, but it's a random object, so here it's just an instance of this object. Okay, so do I take the time to tell you why the square root singularity is the most universal universality class? Maybe yes, because it's a good thing for students to practice. So square root singularity is the most universal universality class. The reason is that you have a functional equation like the one I had for trees, where t equals 1 plus zt squared. Okay, so let's put a minus like this and say this is 0. So this is phi of z and t. Okay. So you look at the 0 level of this equation, and basically what you can use is the implicit function theorem. So you will look at the differential along the curve given by t of z. Okay, so you look at this equation, expand in coordinates, so you get d phi by dz plus blah blah blah, and the important object here is this. This is what you want. You want this. Okay. So it's cool because here it's linear in this quantity, so you can extract it, but you need this derivative to not be 0 for this to be possible. So in particular, when this is 0, when d phi by dt is 0, it means that you have a critical point. You cannot inverse the curve anymore. So it's like you have a vertical tangent in the curve. Okay. So when you hit such a point, you can perform a Taylor expansion around the critical point ZCTC. And so you have the evaluation of phi at this point. And then you have first order. So this is 0 by assumption. Then you have first order term in Z minus Z critical. You think you would have a first order term in T minus TC plus T minus TC. But no, because you're at a critical point where d phi by dt is 0. Okay? Because here there would be d phi by dt, which is 0. So when you perform the Taylor expansion, you have to go to quadratic order, to second order in T minus TC. And so eventually you get, schematically, you get something like Z minus Z critical behaves like T minus T critical squared. So then you take a square root and you have your square root singularities. So this is why it's very universal, because it just happens when you negate the implicit function theorem. Okay? But there are exceptions like combinatorial maps. Okay, so before we go more into maps, I have some basic properties of maps to give you. First, the genus, which is a topological invariant, it's determined by Euler's formula. And there's this book by Moha and Thomassen that you can have a look at. And a large part of the book is dedicated to proving this Euler's relation in full generality. So F is number of faces. Here it's edges. And V is vertices. And H is genus. Vertices, it's weird. Okay. So from a more combinatorial point of view, if you specialize to triangulations, you can say, okay, let me forget about the genus, which is a topological quantity. What this tells me, because H is positive, it's non-negative. Because H is non-negative, you have a bound on the number of vertices, which grows linearly with the number of faces. So this will be very important for us. Linear bound on the number of vertices. Okay, so we can do a proof, but basically, yeah, it's almost done. You take the fact that H is non-negative, and you need the fact that for triangulations, 2 times the number of edges is 3 times the number of faces. Okay, so if you count edges, 2 times the number of edges, it's like counting 3 times the number of faces. So it gives you this relation. In particular, in 2D, there's this equivalence that the sphere is like having genus 0, and it's like maximizing the number of vertices at fixed number of triangles. So if I try to maximize the number of vertices on my surface, it has to have genus 0. So basically, you have a combinatorial statement that implies a topological constraint on the genus. But this is not true in higher dimensions. So this is very special. Now let me show you how you can count planar maps. So we're around half my material. So that's good because we're around half the time. So I will consider rooted maps and planar maps. So rooted means that they have an oriented edge like this. And the root face is on its left. So the root face here is the exterior. Okay. And it's obviously planar here. On this picture, you can see it's planar. Now, to simplify the model, I will take some particular values of tk, which are t to the k over 2, where tk, remember, is the weight of a polygon of size k. So here it would be t4, t4. I have lots of t4. It's t2, and so on. Okay. So this will simplify things a little bit because what it gives me as a generating series is the sum of a rooted planar maps of t to the number of edges. Okay. So basically, by taking this particular value of tk, I only count edges. So it will simplify things a little bit. Now, these objects, these planar maps, they were studied by Tutt in Waterloo, Ontario, at the University of Waterloo in the 60s, in the context of the four-color theorem. So obviously he did not prove the four-color theorem, but he found some really beautiful things about planar maps. So to count them, to find the generating series, I will need to keep track of the length of the root face. Okay, root face is on the exterior. So say it has size n. There are two possibilities when you look at the root edge. So here is the root edge. So either it's a bridge, meaning that if I remove it, I have two connected components, which are disjoint. One has a boundary of size n minus k, and the other has boundary of size k. Okay, so this is case one. The second case is when I remove the root edge, I have only one connected component, and basically it means that I had two faces on each side. So the root face here and a non-root face here. Okay, and now they are merged. Okay, it just becomes a single face. And this face has a new parameter, a new size, which is n plus k minus 2. So this is the second case. Now, it means that if you have a map of boundary size n, it can have two contributions coming from 1 and 2, and you can write them explicitly like this. First term is quadratic because there are two connected components in case 1. Okay. Now, this is a very difficult equation to solve. Okay, just try to write it down and think about it. It's very difficult. So what you have to do is introduce a generating series for this, meaning that you have a parameter x to the size of the boundary face, the root face. Okay, that's called the catalytic variables. And what I'm really interested in is the value at x equals 1. So when I forget at x equals 1, you see I forget about the size of the root face, the boundary face. So, so when I transform my previous equation using m of t and x, I get this equation. So it's quadratic, it seems nice, but there is a nasty quantity here, which is called the divided difference. And you see that because of this term, I cannot evaluate the equation on x equals 1. Okay, I cannot do it. So this term is well defined at x equals 1, but I do not know what its value is. Okay, it is well defined because the numerator has a factor x minus 1, but I don't know its value. So to solve this equation, you have to be extra smart. And you can prove if you are very smart, you can try this by yourself. It's not dangerous, but it's difficult. So you can eventually find a quadratic equation for m of t. And because it's quadratic, you can solve it, and you find that you have a square root here. But inside the square root, there is 1 minus 12t to the 3. So it's not a square root singularity, it's a 3/2 singularity. So if you want details on this, there's a physics review by Di Francesco, Paul Ginsburg, and Jean-Zim Justin, which is like a super famous review on matrix models. Okay, so then when you have this explicit expansion, you can apply transfer theorem or just expand, and you find that because it has a 3/2 singularity and not a square root, the critical exponent is different. So here is the critical exponent in the asymptotic. So this is called the universality class of pure quantum gravity in 2 dimensions. And here is a simulation by Igor Korczemski, the probabilist in Paris. And there are lots of 3D rendering on Jeremy Bettinelli's page that you can go to, and so you can move around those triangulations of the sphere. So they look weird, but they are really spheres. They really have the topology of the sphere, and they're also very fractal. Okay. So this is a fractal object that you get in the continuum. And here's a here's a list of the type of geometry. I mean, the types of random objects from combinatorics that are, I mean, it's just a sample, not everything that's, probably everything that I know, but many people would know more. So trees have this asymptotic n to the minus 3 halves and Hausdorff dimension 2. So here it's Hausdorff dimension. Can't try it. Okay, Hausdorff dimension 2, scaling limit is continuous random tree by Aldous. So in the planar case, which is the case of this picture, here it's called the Brownian sphere. And so it was proved, I think, in the early 2000s by mathematicians. And it has Hausdorff dimension 4. It's very fractal, as you can see in the picture, in fact. So topologically, it's a two-sphere. It's really homeomorphic to the two-sphere, but geometrically, it has Hausdorff dimension 4, okay, because it's very fractal. Now, if you want a huge problem, like, you know, you have solved this, so you might get confident, maybe, and try to decorate planar maps with the Ising model. And there is a conjecture: 7 plus square root of 97 over 4 as the Hausdorff dimension. Very difficult problem, as you can imagine. Okay, we have
a question, Valentin.
Yeah.
In the case of the Brownian sphere, yes, geometrically, what is the thing that scales as n to the minus 5
distances? So distances scales. But distances scale like n to the minus 1/4.
And the 5/2, what is it?
Well, the 5/2 is because, let me remember. So it's very much related. The 5/2. The 5/2 is basically the entropy. So it tells you how it's a critical exponent for how many of these objects you have. But yes, if you want to know how distances scale, you have to, yeah, you basically, so you take a point and a ball of radius r, and you want to know how many points you have in this ball of radius r, something like this. So you're right. In fact, it's not really related to the exponent, to the critical exponent that I gave you. I mean, maybe it is, maybe it's not. We don't really know.
Okay, thank you.
Okay, there's a Watabiki conjecture or prediction that gives you a Hausdorff dimension in terms of C, a number here, which is called the central charge, because everything here is in fact related to conformality theory, but I will not explain. So, like, that's quite a lot already to digest in 2 dimensions. So I won't go further into it. If you have questions, we can take like a few seconds to write and answer them. So otherwise, that's all I wanted to say in 2D.
Okay.
So let me go to higher dimensions.
Yeah, perfect. You still have, just to let you know, 40 minutes.
Yes, thank you. So let me go to high dimensions. It's very difficult because the topology are not as simple as 2D topologies, which are classified by a single integer, the genus. Here it's not the case. There's an approach called matrix integral, matrix models, that I will we'll talk about more later, which makes it possible to use eigenvalues of matrices to solve everything that I told you about. So here, those equations, you can get them from eigenvalues of matrices. It's quite beautiful. But you cannot do that in high dimensions, because what you're going to do, if you have tensor integrals, you don't have eigenvalues. So tricky. Also, okay, the genus is basically the Euler characteristic, if you're familiar with that. Otherwise, you can just not listen to this sentence. But so you might say, okay, let me look at the Euler characteristic in high dimensions. But in fact, for all orientable three manifolds, it's 0. So it won't classify anything. So basically, it's very difficult to deal with topologies in 3D, let's say. So instead, what we did was to look at some combinatorial classification. And remember, so this equation here comes from Euler. And basically what we want to do is generalize it to saying that the number of d-2 simplices, so here it's d-2 simplices, satisfies a linear bound with respect to the number of d simplices. Okay? So that would be a combinatorial generalization of Euler's formula. And we sort of know things to expect from numerical simulations, which are called dynamical triangulations in the 90s. Jan Ambjörn, Renate Lal, Jokiewicz, this group of people. They did numerical simulations, but can we do more than numerics? And which set of triangulations can be useful for this? So I will use something called color triangulations. But hold on, because you know that 3D gravity is topological, meaning that we can just use one single triangulation, and the physical Hilbert space will be isomorphic, whether you use the continuous theory or just a single triangulation. Okay? And you can evaluate transition amplitudes on a single space-time triangulation. So there are lots of papers about this. And different triangulations will be related by gauge symmetries or diffeomorphisms. So it's useless to look at different triangulations because just one is enough. The others are just gauge transformations. But that won't be the case in 4 dimensions. So in 4 dimensions, you might want to take a continuum limit by some coarse graining process. And that would involve embedding so you have Hilbert spaces on the boundary, which are spin networks, and you have to relate the Hilbert spaces depending on the way the boundary triangulations evolve. Okay, so it's something a bit similar to tensor network renormalization that's been studied by Bianca Dietrich, Sebastian Steinhaus, and other collaborators of them. I'm sorry because probably missing a lot of people. If some people in the audience know about people that would be deserved, that would deserve to be cited, and I forgot, you can just write in the chat. I'm sorry. So other questions are, do we want, so if we think about spin foams, we have to sum over spin foams in the bulk, but then what do we do on the boundary? Because we want to recover some continuous picture, like a metric picture. So we have to take also some kind of continuum limit on the boundary, and that's what I was mentioning from the work of Bianca Dietrich, Sebastian Steinhaus. So I think it's a good question. Because of the 4D case, which doesn't work like in 3D, it's also a good question to ask whether in 3D you can, instead of considering it as directly as topological theory where you can work on single triangulation, instead of that, you say, okay, let me try to use an approach by summing over triangulation. Okay. That's related to Gromov's question. I will probably mention that later. So I want to tell you about colored simplices. I think it's interesting exercise to understand them. So a colored simplex is basically a simplex where the faces are colored with a color from 0 to D. So here's a colored triangle. Here's a colored tetrahedron with color 0, 1, 2, 3. Now, so the faces are colored 0, 1 to D, and the edges of the triangle, so the vertices of the triangles is shared by two edges. So you can label it with a pair of color, okay? And here is the case of edges of the tetrahedron. So it's shared by two triangles. So it's labeled by a pair of colors, okay? Depending on the dimension, I can continue this process, and like D-3 simplices, which are here vertices, they are shared by 3 triangles here. So they are labeled with a triple of colors, okay? So D-3 simplices labeled by triple of colors, and in fact, colors identify all the subsimplices. So this is very important because it allows to define a unique attaching map, which is a way to glue simplices together. So remember, we're trying to define gluings of simplices in a way that we control enough so that we can count them, okay? So we can enumerate them, control the topology, and so on. So it's important that we control the way we glue them. And the way to do it with colored simplices is very simple, is that you identify faces which have the same colors. But if you just say that, you might have several ways to do that, because you send this vertex to here or to here. Well, you do it in the way that respect all the subcolorings. So this vertex has a pair of label, which is the pair 0, 1. So you have to send it to the other vertex of color 0, 1 on the right. So do not map it to 0, 2. 0, 2 on the left is mapped to 0, 2 on the right, okay? So you look at the colorings of the subsimplices, the subcolorings. Okay, here's for tetrahedra, 2 tetrahedra glued along the triangle of color 0, and you map the edge 0, 2 on the left to the edge 0, 2 on the right. And for this to be uniquely defined, you map the vertex with colors 0, 1, 2 on the left to the vertex of color 0, 1, 2 on the right. And that uniquely defines, so here the word is unique, uniquely defines the glue. So because the gluing is uniquely defined by the color of the faces, you can just say, okay, so let me represent my tetrahedra by vertices. So I have 2 tetrahedra, I draw vertices, and I say, okay, when they are glued along the triangle of color 0, it means that I wrote an edge of color 0. So here it's the glue. Okay, so basically I can just, instead of drawing tetrahedra, which would be a nightmare, I can just focus on the gluing. I can just focus on the graph, okay? And if you think about this graph, is basically the dual graph, or the one skeleton of the dual triangulation, of the dual complex. So it means that inside of each tetrahedron, you add a vertex, and incident edges correspond to the triangles, to the faces of the tetrahedron. Okay, so a D simplex gives you a vertex, D-1 simplex gives you an edge, and so on. So how does it work when I say and so on? It means that D-2 simplices, they have 2 colors, remember, they correspond to a bicolored cycle. D-3 simplices, they are labeled with triples of colors, and they correspond to tricolored connected components. Okay, so let me just show you a nice picture. Here I have 6 tetrahedra glued along an edge in the middle, which is this edge here. Okay, and when I take the dual, so yeah, what I want to say first is that so it's labeled, this edge is labeled by a pair of color, let's say yellow and blue. Now my colors are real colors, so yellow and blue. So when you go around an edge, you meet yellow, blue, yellow, blue, yellow, blue, you alternate like this. And when you take the dual, you have a bicolor cycle, okay? Bicolor cycle. Okay, the same works with D-3 simplices. So let me show you an example here with the octahedron. So here on the left is an octahedron. It has 8 tetrahedra, and believe me, there is a color code that I spent a lot of time to get right. So the colors are blue, yellow, and some kind of pink, reddish pink. And when you see green, it's because it's blue behind yellow, okay? So there is a color code. Now, all the boundary triangles have color 0. All internal triangles have color 1, 2, or 3. And there is a single internal vertex here, which has the triple of colors 1, 2, 3. Okay. Now, if you take the dual picture, the dual of the octahedron is the cube, obviously, and you'll see that it has only colors 1, 2, and 3, and the color 0, they correspond, they are dual to the boundary triangles, dual to boundary triangles. Okay, so dual to, so basically the vertex that's in the middle of the octahedron is represented by the cube. And so this is my generalization of polygons to higher dimensions. They are objects that are made of tetrahedra, where all the triangles of color 0 are on the boundary. Okay. So I call them bubbles because they are not always homeomorphic to balls. So I cannot call them balls, I call them bubbles. And so here's an example, which is the octahedron. But there are many others. And thanks to that, we can investigate universality, which means we can study gluings of different building blocks, okay? So these here, I call them colored building blocks. And in the dual picture, I call them bubbles. And when I say I, it's just people in the community. Okay, so I think I will skip the how we recover the 2D case, but we do. Basically, you take a gluing of polygons, and what you do is you add a vertex in the middle, and then you can add the proper colors. So I think it's probably a good exercise to do it. So you take the slide, which will be online, and you try to do, and you just look at the pictures and try to understand what happens. Basically, what happens is that the polygons have the colors 1 and 2, and the color 0 is used to glue them. Okay, so here I wanted to give you the bubbles with only a few vertices. So let me do that. So 2 vertices, there's just one bubble, which is like this. So it has color 0, 1, 2D. So basically 2 simplices where I identify all their faces together. Okay, and that's a D sphere. So if you find it hard to visualize, well, I can't help you because it is indeed hard to visualize. Okay, like you really have to, if you want to do it properly, you really have to say, okay, it's I take 2 simplices, so you can think, you can write them as as balls, simply shelled balls. And then when you do the identification and try to prove that it's a sphere, you can do that mathematically, but it's indeed hard to visualize. So ad equals 3 with 4 vertices. So you take 4 vertices, meaning 4 simplices in the dual. And so let's say the color 1 goes here, so here. Then the color 2, because I want something connected. And then for the color 3, I have several options. It can go either like this, or like this, or like this. Okay. And there's another solution. So there would be 1, 2, 3, 3, 2, 1, 2, 1, 2, 1, 3. And there's also obviously this, where here is 3 is alone and 1 and 2 are like this. Okay. So these are gluings of 4 simplices. Okay. At d equals 4, you have more guys because you can do that obviously, just like before, with one additional color because it's at d equals 4. You can also do that. Okay. So basically, what I want to say is that there are more and more building blocks available with the dimension. Okay, so when you try to work with those objects, it's much more convenient, like I say, to use the graphical representation instead of drawing tetrahedra, for instance. So in 3D, you have basically graphs where each vertex represents a tetrahedron. So it's a tetrahedron. And each edges represent a triangle. And they are colored. Here, the dashed lines is color 0. Okay. Dashed. So here I have the 3 orange components are the bubbles with color 0, with colors 1, 2, 3. It means that in this triangulation here, I have 4 vertices of colors 1, 2, 3. Okay, because I have 4 connected components, 4 bubbles. There is a quantity that will play an important role, which is the number of bicolored cycles with a color 0 and something else. So why? Because they are dual to d minus 2 simplices. And you know that d minus 2 simplices carry deficit angles in Regge calculus. Okay. So here's an explanation of why we are interested in those d minus 2 simplices because of Regge calculus. So here's the Regge action that I already wrote. And the usual interpretation in dynamical triangulations is to say that we have equilateral Regge, meaning that all simplices are regular. So the volume is fixed. The volume of each simplex is fixed. Also, the deficit angle becomes proportional to the number of simplices around the d minus 2 simplices, sigma d minus 2. Okay. Simply because the simplices are equilateral, so all dihedral angles are fixed. So deficit angle is just proportional to the number of guys around it. So this suggests, so if you think about the Regge action in terms of equilateral objects, you have basically a coupling T to the number of d simplices and n to the number of d minus 2 simplices, which accounts for the Regge, for the curvature term with deficit angles here, and here for the volume part, basically, roughly. So it suggests to count our object with respect to the number of simplices, which in the dual are vertices, and the number of d minus 2 simplices, which in the dual are bicolored cycles. Okay. So there are some theorems about those objects, but maybe I will skip this because you would just get overwhelmed with theorems. So instead, let me tell you about this because I think it's interesting. This is a question that's sometimes called Gromov question, but obviously it was known well before Gromov. It's just that Mikhail Gromov is a famous mathematician and he popularized the question by saying, oh, it's interesting, and because he's famous, people started to look at it a little bit more. So the question is as follows: is the number of 3D triangulations of the sphere, so the sphere S3, is this number of triangulations exponentially bounded with respect to the number of tetrahedra? So basically, number of triangulations, so say Tn with n tetrahedra, is it bounded exponentially? So like k to the n times some constant. Okay, if not, I mean, if it's true, that it means that it's a summable ensemble, okay? Because you can sum, because the right-hand side here is a geometric series in n, okay? So it means that you would have a summable ensemble, and it makes sense to consider generating series and partition functions. But if it's not summable, I mean, if it's not exponentially bounded, that it might not be summable. And then it means that summing over triangulations of the sphere has no sense, no meaning. Okay. And so far, there was a bound by Rivasso, which was n factorial to the 1/3, and it was refined by Chapuis and Per-Arnaus, who are combinatorialists, to n factorial to the 1/6. But it's still not exponential, you know, it's still factorial. So like this is a very, very difficult question and very important for physics, I think, because otherwise it doesn't make sense to sum over triangulations, whether you want just to count them or whether you want to add spin forms on them. It's a critical question. So one of the theorems that I was quite happy to prove, and obviously I won't do it in this lecture, but I want to to give it to you because I think it's the more general theorem that we have. It's about the enumeration of 3D triangulations with those colored building blocks. And it's very general because you take any set of colored building blocks which are homeomorphic to 3 balls. So anything homeomorphic to 3 balls. And you glue them and you ask, how can I maximize the number of edges? So remember, number of edges is in 3D, these are edges. Okay, so maximizing the number of edges means maximizing the curvature in 3D. And you can prove 2 things. The first thing is that those triangulations who maximize the number of edges, there are 3 spheres on the topological side. And on the combinatorial side, there are trees and bijection with trees. Okay, so topology is nice. Combinatorics is nice, but it's almost too nice. In fact, it's kind of trivial eventually. So it's a very difficult theorem to prove, but the answer is kind of trivial. And it's like I say, it's very difficult in 3D to get models which are both solvable and non-trivial. Okay, so here it was hard to solve and eventually a little bit trivial. And so should I talk about this? Let me think about what I still have to show you. I think I will skip this. Let me just take a minute to think. Okay, I think I might not be very late if I just skip a few things. So let me just give you one example of the kind of triangulations that come up when you try to maximize the number of edges in dimension 3. So these are graphs which are called melonic, and they are built like this. So you start from the guy with 2 vertices. So in 3 dimensions, it has color 0, 1, 2, 3. And then you take any edge of color C and you perform the melonic insertion, which is this. Okay. So when you do that repeatedly, so iteratively, you get a graph like this. So this is an example. Remember, dashed lines have color 0. It's just convenient to do that, but you don't have to care about it. So the topology is the sphere, and the scaling limit was proved to be the continuous random tree, which is not surprising because in my theorem I tell you that you have a bijection with trees. And you can count them by saying, well, let me look at the 2-point function. I mean, we don't have field theory yet, but it's basically a GFT in fact. And so if I look at the 2-point function here, I can have any melonic graph inside. And either it's a bare thing, like this, or it has a vertex, but because it has to be melonic, it has to have this structure here, where inside every edge, I can reinsert the 2-point function, and then I can reinsert it on the right-hand side. So it gives me an equation G equals 1 plus t squared, because there are 2 vertices here, t and t, so t squared, and G to the d plus 1 in general. So this is like the equation that I had for binary trees, except with a higher power, but they are still trees. So in fact, it's very different from the 2D case. Remember, I had the universal class of trees and the universal class of planar maps or 2-dimensional gravity, and they are very different. Both very fractal, but very different. Okay, so far we haven't been able to reach new universality classes. We have reached others that I haven't told you about, but we have not reached new classes. So this is because, as I said, it's very difficult to have a model that's both solvable and interesting. But we can still have applications beyond the purely combinatorial models that I showed you, because those models, they don't have spin degrees of freedom, they only have graph degrees of freedom. So what if we want to have some group quantum gravity amplitude and GFT applications? So in fact, it will work because colored graphs are generated by tensor integrals. So I think I have time to show you this. It works like this. So if you take a bubble with d colors, like this one, colors 1, 2, 2, 3, 1, 3. And to each vertex, we associate a tensor phi with indices A1 and A2, A3. Okay? And for each edge of color C, we associate a tensor contraction like this. So you have 2 phis here and here. If they are glued if the 2 vertices are glued along an edge of color C, it means that you contract the index that's in position C. Okay, position C. Equals 1, a C from 1D. Okay, so for instance, the bubble with 2 vertices that I have shown you, which is a sphere, corresponds to this quadratic contraction of tensors. Okay, phi with all indices identified. So now, what is a tensor model? It's an integral where I choose a set of bubbles P, and I built a polynomial from them, like I just explained with those rules. I built a polynomial, and I put them in the exponential with some Copley constant. Okay. So this is a partition function for tensor models. And basically the result is that if you do Feynman expansion, so you take the interaction. So this is the quadratic term. And these are interactions. So the interactions, they are basically building blocks, which was, colored building blocks or bubbles in the dual. So when you expand the exponential of the interaction, you get many bubbles of different types. And then what you have to do is perform Wick contractions. So basically you add propagators between the phi's and you give them the color 0. So do I have an example? I have this example here. So all the orange guys are the interactions of the model. They correspond to bubbles. And the dashed lines are the propagators. Okay? When you do a Wick contraction between a T and another T, you add the propagator like this. Okay? As a result, you find that the free energy, log of Z, is the sum of her connected colored graphs. And if you follow the identification of indices along Wick contractions, you find that you have a n for each bicolored cycles. So this is really like what people did in dynamical triangulations. Now it also works for GFT. So let me go straight to GFT here. So what is a GFT? You start with a field phi of G1 to GD, which is on D copies of a Lie group G. Okay, that's a Lie group. And you apply Peter-Weyl theorem that you probably heard of in this week or the week before, meaning that you expand phi, you do a sort of Fourier transform, you expand phi into modes because the representations, the irreducible representations rho of the Lie group G gives you a basis of functions, basically. So you have here the modes, Plancherel or Fourier modes if you want, of the expansion. So is it like the framework that I just described? Well, it certainly looks a bit that way if you rewrite things a little bit and you say a triple of representation rho and matrix elements ij in this representation, you say that's a multi-index A. Just a notation for this triple of indices. And you add a cutoff to the number of representations, and that's basically your tensor. This guy with corresponding to the modes of the field gives you a tensor. So what are the weights associated to bicolored cycles? In tensor models, you have just n. In the Bulatov-Oguri model, you have some delta of the Holomies because of flatness. And if you expand on two modes, which is what I just told you to do, and you add a cutoff, you will find that it scales like n to the 3. Okay. Now for more, so basically you have some kind of control on the weights. But in more complex pinform models, you have, when you expand to modes, you have something like sum of j from 1 to n of some function of the Holomies. And this function, is it bounded? Because if we, basically this symbol here means bound. So is it bounded? It sort of has to be, otherwise it's going to be very difficult to say anything. So what I mean, what I want to say with this table is that basically everything behaves similarly. If you look from far away, you have n here, n to the 3 here, and maybe if this is bounded, then there is some n to some alpha, okay? So it means that even if you don't have a tensor models or a Bulatov theory, but if you have a more complex pinform models, you still have some sort of heavy weights on the bicolor cycles. So in 3D, there will be the edges. Okay, and you can control everything in the Bulatov-Fuguri model, but in general, it's difficult to conclude because this function, whether you have to know if it's bounded, if it's positive, because it might not be, and there might be interferences like cancellations. So it's difficult to say anything. I will skip this exercise, which is nice, that I took some time to prepare. Let me just go straight into group field theory and its renormalization. So let's say we can perform the sum over over spin forms, over the bulk triangulations. So there are still a few things that we would like to do. Is first to remove the cutoff, which means we have to study some renormalization group flow with respect to spins. We also have the boundary issue that I told you about, because basically, look at those pictures. Here it's a Feynman graph for the scattering of 4 particles with some fixed momentum. It's perfectly fine in particle physics because you might want to study the scattering of 4 particles. But if you look at the similar picture that I showed you at the very beginning of the lecture, where you have 2 spin networks and a spin foam between them, I don't think it's very fine for quantum gravity, because this does not represent any quantum metric. It's very degenerate, as we say. Okay, so this is a point that's been emphasized, that you have to also evolve the boundary triangulations, like in a renormalization group flow. So this is something that's difficult to address, and I won't do that here. Instead, I will look at the Bulatov model, where Edward Wilson-Ewing probably told you it's a GFT whose amplitude are Poisson region model. But they are typically divergent, and these divergences, they come from gauge symmetries. So here it's a small example where you look at the 2-point function in the Bulatov model. So you have phi of 3 group elements and a phi of 3 different group elements, and the 2-point function starts with a Baire propagator. And then you have a radiative correction here, which is the elementary melon that I told you about. Okay, so I'm skipping the calculations, but when you look at these elementary melons, you have to integrate over 3 holonomies, which live on the edges of the elementary melon. And then you have a weight on the bicolor cycles, which means that the holonomies are trivial. There's no curvature. It's the flat theory, the Bulatov model, remember. But there are too many deltas, because this one enforces H1 equals H2. The second one enforces H2 equals H3. And then the third one enforces H3 equals H1, but it's also enforced by the first 2 constraints. So you have a divergence, because you have to evaluate delta of 1, and it's divergent. And you need some regularization. So the loop quantum gravity perspective is that there are too many delta functions because of gauge symmetries. And I won't have time to tell you more about this, although I would have liked, but maybe it was given in some previous lectures. However, in the field theory perspective, you don't think of the divergences as gauge symmetries that you have to gauge fix. Like, it seems very hard to do. Maybe not impossible, but very hard. So instead, use a cutoff. So it means you regularize the delta on the group with something like a heat kernel at small times. Okay, so it looks very much like a delta, but it's regular. So it regulates small distances on the group, which, remember, in loop quantum gravity corresponds to a cutoff at large spins. Okay, so from the point of view of the geometry, it's like the large scale geometry that you regulate with the cutoff. And there is a theorem that we proved with Joseph Benjeloun, that the Bulatov model is not renormalizable. And in fact, it just comes from applying this regularization to the elementary melon, And what you find is that at leading order, you find the bare propagator times some divergence factor. So it's a mass renormalization. You can reabsorb this divergence into the mass of the theory. But next to leading order, you find some Laplacian. Here it's the delta is the Laplacian. So you find some Laplacian acting on the propagator, which means you have a wave function renormalization, which means you have to add a counter term with Laplacian to the theory. And if you remember the lecture by Edward Wilson-Ewing in the Bulatov model, there is no Laplacian in the theory. So you cannot add a counter term for this divergence. So that's why it's not renormalizable. So what you have to do, and I'm basically done. This is this slide and a conclusion. So what you have to do is you have to add the counterterms that you need first in the original theory and redo the whole analysis. And so these kind of things have been called tensorial group field theory here. And there's an interesting model that's due to Carrozza, Oriti, and Rivasso at d equals 3 and with the group SU2. So it's very much like the Bulatov model with a non-trivial propagators. And they have shown that the interactions up to order 6 are just renormalizable. So, so it's a very, very difficult analysis that they were able to do for this type of Bulatov model. There's a review by Sylvain Carrozza that I invite you to check. It's called Flowing in Group Field Theory Space. 2 obligatory comments. Some models are actually asymptotically free, which is like amazing from the quantum field theory perspective, because like we know a QCD to be asymptotically free, which is a difficult theory. It's a non-abelian gauge theory. And here you also have asymptotically free theory, but they are obviously non-local, if you remember Edward Wilson-Ewing lecture. So if you want to understand why they are asymptotically free, I invite you to check this, this short paper, 8 pages by Vincent Rivasso, Why Are Tensor Field Theories Asymptotically Free? It's just some combinatorics with quantum field theory. It's beautiful. What are the physical implications of those renormalization flows, which are kind of abstract? I do not know, and I don't think anybody really knows. Let me just, before I conclude, say that the way it works is because the divergent graphs are spheres, because they are melons. So they are graphs that I was able to understand through my combinatorial analysis. So without this combinatorial analysis, it would have been very difficult to get this renormalization of the Bulatov model. And because they are spheres, you know that the flatness constraint implies that it's picked on trivial solutions for the holonomies, and this will make the renormalization of the GFT possible. Okay, so just a quick conclusion. I insisted quite a lot that loop quantum gravity had 3 types of degrees of freedom, like spins, boundary triangulations, and bulk triangulations. And I insist, no, not triangulations, but bulk graphs and boundary graphs. And I insisted quite a lot also to make the case of triangulations, because they are both graphs, so you can use loop quantum gravity on them, and they also capture topology. And I think they are necessary to recover the metric in the continuum. So I showed you different models and different quantizations, whether the models has no spins, but you sum over all graphs, or in 3D loop quantum gravity where you have a single triangulation and you sum over spins. I didn't really explain that one, but I mentioned it quite a few times. So these are different models with different quantizations. We're still looking for new universal classes in dimension greater than 2. It's very hard, but we are able to prove theorems, so it's quite good, at least. We are now able to classify renormalization tensorial group field theories, and we have asymptotically free theories. there's a difficult interplay between all the types of degrees of freedom in loop quantum gravity that's still very difficult to deal with. And in addition, if you really want, you can try to add simplistic constraints which break gauge invariance. You have to flow the boundary, the space of boundary states, and you have to wonder whether the divergences come from gauge symmetries or not. So if you add all this, you get yourself quite a challenge for a few decades, I guess. So thank you for your attention.
Thank you very much. Thank you very much, Valentin, for
Sorry for the delay.
We have no problem. We have 5 minutes for question, if there are some. So
can I ask a couple of questions if there are? Oh, let's give priority to students, please. Mine are just curiosity. So.
Maybe if you ask one, it will give time for
Okay.
other
so
to
there
think
is one
about their
already.
questions.
Yeah, but there is one already by
Yeah.
Ong Waitan. If you want to unmute yourself, Ong Waitan, and ask directly your question.
Color here is not the eigenvalue of the spin operator. No, it's more of a tool that we use to define the gluing of building blocks. So building blocks homomorphic to, so the building blocks, they have a boundary, so they are homomorphic to balls. For some of them at least. And when you start to glue them, like if you take, let's say you're in 2D and you take two triangles, you identify all, you identify 2 by 2 their edges. Okay, so you get a sphere, right? You get a sphere with, and the equator is basically the 3 edges. Okay, so this is the picture you can get in 2D. In 3D, it's more difficult because basically what you're going to do is have 2 tetrahedra and you want to glue them together. So the colors here are just a way to define the gluing. Okay, it has nothing to do with loop quantum gravity itself. Okay, if you go back and look at the slide, in fact, I'm not really doing loop quantum gravity. I'm just thinking about the combinatorics of the triangulations. And I really wanted to present this model of color triangulations because this is like the only model we're able to do calculation with. So it's just a way to define the gluing of objects. Okay, so I hope it helps.
Yeah, thank you. There is another question by Beat Chandra Hongol. If you want to unmute yourself and ask it.
Hi. So please correct me if I say anything wrong in my question. So from what I understand, you have attributed some definitions to graphs, physical definitions to graphs, and then the theory is trying to develop this and connect it back to physics. So, so my question is, can we have any physical intuition about gluing? So are these, I remember you were shortly explaining, they are like propagators, but do they have more meaning to it? And
it's, in fact, it's more of a mathematical questions. The reason is that usually if you, I mean, I don't want to make too many generalities about what people do in quantum gravity when I haven't read all the papers. But like when I would write paper in quantum gravity, I would typically say start with a triangulation. Okay, and so let delta be a triangulation, let gamma be its dual, and you have spins on the edges or on the faces if it's a spin form. But this is a context where you fix the triangulation. But in loop quantum gravity, in fact, you can't expect the Hamiltonian constraint to not change the graph. Okay, that would be probably naive, I think. So you have to expect operators like the Hamiltonian constraint to change the spin networks. So it means that you have to understand how graphs can change into other graphs. And you can do that, obviously, eventually we want to do that with operators like the Hamiltonian operator. But at the purely mathematical level, which was the beginning of my answer, at the purely mathematical level, you have to understand how you built a triangulation. And the way to do that is, for instance, let me go back to the 2D case, is that you take some building blocks, like here, polygons in 2D. You take some polygons and you glue them. Gluing them means just that you take a tube of glue and you add some or tape, and so you put some tape here, and you know, you stick one to the other, and from two building blocks you get a larger guy, and so on. And so eventually you get a surface on the right here. It's a surface. So usually what people do in loop quantum gravity, they say, I have a triangulation, and that's the right-hand side. What I do here is I try to understand how you get to the right-hand side from basic objects. Okay, so the gluing is not physical. It's just a mathematical way to define the final objects I want to work with.
Okay, thank you.
Pietro, would you like to ask your question?
Yes, they're very quick, so I think we have time. So first, there are two curiosities. There are more than questions. So first, all the examples that I saw in the literature of QFTs are based, the concrete examples are based on compact groups like SU2 or U1.
Yes.
Are there versions for non-compact groups?
Yes, but it's going to be disappointing for you because it's like Z.
Okay.
Wait, I have to think. So if you think of SL2C, no.
Okay.
Definitely not. Yeah.
Okay.
So yeah, here you want to the D or SU2, and that's basically it. Yes.
Okay. Then the second question is even probably faster. So you say that to study divergences in GFTs, you need to regularize the bubbles divergences that we have in some way and then compute. So there are, if I think about QFT, there are many ways to regularize divergences. No, there's dimension regularization, there's Pauli pillars, there's mass regularization, whatever you want.
Yeah.
Are there a study? Is there a study in how many different ways I can regularize bubbles in GFTs?
So the paper by Carrozza, Oretti, and Rivasso uses a heat kernel.
Yeah.
I know that Sylvain Carrozza has some articles, some papers where he uses dimensional regularization.
Oh,
which is interesting which is interesting because it interpolates between SU2 cross U1, which has dimension 4, and just SU2, which has dimension 3. So he uses, I think, 4 minus epsilon.
Okay, cool, very cool. Thank you.
Vinicius Silveira has a last question. Vinicius, you can unmute yourself.
Yes. Okay, yeah, interesting. It's okay. I've read the question. Yes, interesting. So you would have to ask an expert in both group field theory and quantum groups. I can think of one expert of both, who is Florian Gerali in University of Waterloo. I'm not sure. I mean, yeah, yes, I think you can. Like if you look at Oguri's paper, so Oguri, so he has lots of papers. You have to look at his early career before he went into string theory. Oguri's paper is with 15 J symbols for SU2Q. So yes, but is it mathematically clean? Not really. So I would still ask an expert to check if everything really makes sense. However, I think what your questions might have as an underlying question is about divergences and renormalization. So if you use a quantum group at Q root of unity, you won't have divergences anymore. So that's true. No divergence anymore. So it means that you don't have to renormalize, but you still can, because renormalization is about changing scales. Okay, you can imagine, right? When you do renormalization, you say, okay, this is my 4-point function, and I want when some of the external momenta are at scale, so p at scale m, at a given scale capital M, then I want this to be lambda that are measured in the lab. Okay, and then you do your renormalization between the bare propagator, the bare vertex, to reach the renormalization scale that you want. So you can still renormalize, and I think, yes, it's interesting because it explains how scales, how physics changes with scales, even if there's no divergence. So to answer the question, would this be interesting? Yes.
Thank you, Valentin, and thank you all for attending this course.
Everyone.
So yeah, I think